Okay, welcome to chapter 8, limit theorems. Okay, so given the time limit, we're only going to cover one theorem in this chapter, but it's a very important theorem that I believe if you move on to take more statistics courses, this will become very relevant, and maybe you have taken some already, so hopefully this is going to click to what you have learned before. Okay, so the theorem that we're going to cover is what we call the central limit theorem. Okay, and we're going to cover the definition first and then talk about what it means. And then we're going to go over an exercise. So let x1, x2 to xn, okay, be a sequence of independent and identically distributed random variables. Okay, so what they mean with this term, independent and identically distributed random variables, meaning that x1 through xn, they're independent from each other, okay, but at the same time, they follow exactly the same distribution. Okay, so you can imagine x1 through xn follow binomial, follow the same binomial independently, okay, and you can also think of it follow the same Bernoulli independently, or all of the other distributions that we have learned, like normal, uniform, things like that, and geometric. Yeah, don't forget our geometric negative binomial. Okay, and okay, so what this is saying, the central limit theorem, is that if the random variable has mean mu and variance sigma, okay, then the distribution, so bear with me here, okay, the distribution of the sum of all of the random variables, okay, minus n times mu, okay, so again, it's sum of all of them here, okay, mu is the mean, so n times mean, like it's the average sum, right, in a sense that, well, I have n copies of the different random variables here, and then the mean is mu, and then divided by sigma times square root of n, okay, so this whole term, this is a random variable, okay, don't forget, okay, because we're looking at the sum of the random variables, okay? It's going to tend to the standard normal as n increases or approaches to infinity, okay? So what this is saying, standard normal, don't forget, okay, is the normal distribution centered at 0, okay, with mean 0 and variance 1. Okay, so as n goes up to infinity, of course, you don't need like super large n. I think usually like when n is as large as 30, this result holds. Okay, so what this is saying again, okay, is that we're looking at a particular random variable, okay, where I put in the box here. This random variable is the sum of this n random variables minus the n times mu divided by sigma n square, square root of n. Okay, so this might sound a little bit too vague. Okay, so let me show you like in words what we really mean by that. Okay, so what we are meaning here using the central limit theorem is to say that if we do know, okay, the random variables, they have a finite mean and a finite variance, okay, then the distribution of the sum of the first n of them, okay, that's what we mean by x1, okay, plus x2 plus xn, okay, if you have n large enough, okay, the sum itself gonna follow a normal random variable with mean and mu and variance and sigma square. Okay, so you might be wondering, okay, where does the mu and sigma square come in? Okay, so notice up here, the way that we're introducing it is, well, if we subtract the mean, okay, and divide it by the standard deviation, we say that it follows approximately follows a normal, standard normal, right? So remember all of the stuff that we have learned about the normal distribution, right? We can recenter it and scale it, okay? Meaning that what this is saying is the equivalent of what the English words down there is saying, is that the sum of this first n records is going to follow a normal distribution with n mu as the mean, okay, and then n sigma square as the variance. Okay, so notice, right, we're subtracting the sum, we're subtracting n mu from the sum, right, and then divided by its standard deviation, so it becomes a standard normal. Okay, so it's the equivalent of saying that the first n terms, the sum of them, is a normal distribution with n times mu and then n sigma square. Okay, so this again might still sound vague. Okay, I admit that. But let's go to an example to see that how central limit theorem can be really useful in probability. And like I said, if you move on to take additional statistics courses, a lot of the statistical tests that you'll be learning is based on central limit theorem. Okay, and that's why if you're curious about like when they are saying that n is to be large enough, okay, and that's why we want to have in like large enough samples. Okay, so x1 and xn, you can think of them as observations in a sample. Okay, if n is too small, then this doesn't hold, so you don't know much about like the sum of all of them. Okay, because well, this doesn't hold. But if you have large enough n, okay, then you can actually use the central limit theorem in many different cases, because this is a very important result for n large enough, and then you can say something about the sum, okay, of all of the observations, which can also translate into the average, okay, because if you divide n everywhere, then you're talking about the average. Okay, all right, so let's go to an example, and then in the live session and homework, you will get more exercises here. A person has 100 light bulbs whose lifetimes are independent exponential with mean 5 hours. Okay, if the bulbs are used one at a time, with the failed bulb being replaced immediately by a new one, approximate the probability that there is still a working bulb after 525 hours. Okay, so here again, we didn't get the chance to talk about the exponential distribution like in class, but I think in many exercises you have encountered it. Here I'm including the main information that you need. Okay, if x follows the exponential distribution with parameter lambda, then the expectation of it is 1 over lambda, and the variance of it is 1 over lambda squared. Okay, so what this is saying, okay, so again, so look, let's see. So here we have 100 light bulbs, okay? And then they're asking about, it's still gonna be like working, like you're continuously using them, one dies, and then you start a new one without any intervention, like without any interval in between, okay? The question is asking about what is the probability that it's gonna be working after 5 and 25 hours, okay? So how this is related to the central limit theorem, right? So if we come back to this, okay, so remember the central limit theorem, right, is telling us about how the sum of the first n terms gonna behave, right? When n is large enough, which is in our case 100 for that exercise, is probably good. Like I said, anything greater than 30 usually should be good. Then we are able to use the central limit theorem to think about how the sum, sorry about that, that's my cat, and the sum of them, and then how it behaves. Okay, so we know that the sum of them going to behave as a approximate to a normal distribution. So if we now come back to, sorry about that, if now we come back to this question, then we know that, okay, we have 100 light bulbs, right? And each of them has its own lifetime, okay? We're now curious about the sum of the first 100, this 100 light bulbs, and we want to know whether the sum, what the probability of the sum of it going to be greater or equal to 525. Okay, so again, if we come back here, we're curious about the sum of this going to be greater or equal to something. Okay, we're trying to approximate that probability, and it's useful now because central limit theorem tells us that the sum follows a normal, approximately a normal distribution with mean and mu, and the variance n sigma squared, right? So if we're able to compute the n mu and then n sigma squared, we're able to use the normal distribution that we have learned a few chapters ago to approximate this probability. Okay, so how can we do that? So for each light bulb, okay, notice that the mean is mu, right? Mu is 5, so mu is 5. Okay, so that's good. And sigma square in this case is kind of hidden. Okay, so because for exponential random variables, the mean is 1 over lambda and the variance 1 over lambda squared. So you should be able to get the sigma to be 25 in this case. Okay, so what this is given is that we know the mean and the variance of each xi. Okay, and that's the building blocks, right? Don't forget, we need to get this, we need to get this in order to do our calculation of the normal. Alrighty, so now we can use the central limit theorem. Okay, what we do is, this is a pretty standard way of writing, so I will recommend you to start thinking this way. The question is asking, right? We need to approximate the probability that there is still a working bulb after 525 hours. Okay, so this is saying that we're trying to get the probability that the sum of the first 100 going to be greater than 525. Okay, and then next we're going to write a approximate sign. Okay, this is because all of this is a approximation. Okay, the central limit theorem is trying to approximate it using a normal distribution. So the rest of it hopefully is not too bad, okay, because we're going back to, remember, the standard normal calculation using the z table that we shared. So what this is saying is that we're standardizing it, okay? We're trying to figure out it greater or equal to 525, so it's 525 minus the mean. This mean, again, is 5 times 100, okay, which is the m mu part, okay? And then below it, this is the square root of n sigma square, okay? So we now are able to figure out that this is essentially the probability of the standard normal, right, is greater than 0.5. And then if you go to our z table, you'll be able to find this probability, okay, which is 0.3085. Okay, so that's the probability, okay, approximately probability that there will be a working bulb after 525 hours. Okay, and I will just add one more thing. Notice that because the exponential distribution is also continuous, okay, so we do not need to apply the continuity correction. So here, remember in the past when we're using normal to approximate the binomial, because binomials is discrete, right? So we need to add that continuity correction. But in this case, we don't need to, because this is pretty much just the probability when we're turning this into a normal, and then there's no continuity correction you need to do. Okay, however, depending on the question, which I think you will get the opportunity to practice when you get to the homework as well as the live session exercise, you will see that in some cases, if you're looking at a a sequence of independent random variables, but then of course working using a discrete random variable, then you're supposed to also add the correction. Okay, so yeah, so best of luck. I think this concludes this chapter as well as our entire semester for this course.